by Dr. Professor Ali Sharifi. Ali, please share your screen.
Do you have my screen?
Yes.
Okay, great. So let's start with a very brief introduction to classical machine learning. My name is Ali Sharifi. I'm a faculty member of artificial intelligence and bioinformatics at Sharif University of Technology, and I'm a chair of the scientific committee, International Scientific Committee of Informatics Olympiad, IOI, as well as a member of scientific committee of International Olympiad of Artificial Intelligence. So today I'm going to introduce many topics that are covered in classical machine learning. My talk is towards the mentors mainly rather than students. So there are complicated items there that should be somehow translated into software language that is more understood by high school students. So please regret me if you see some formula, some hard items. Just I want to make sure that many items that are covered in classical machine learning are discussed here. So from Maxim's session previously, you understood that there are methods of clustering. And by clustering, we mean that we have a number of samples, but we do not have labels on them. So this is a kind of unsupervised method rather than the classification that we have the same number of samples, but each sample is assigned to a class. So the idea here is that we want to find out the most similar clusters of samples and put each item or sample into one of those clusters. So we have different types of clustering. There is hard clustering that we want to assign each sample exactly to one of the clusters. Rather, we have soft clustering that it's kind of probabilistic, that we compute the probability of each sample to belong to each cluster. For example, here you see a hard clustering. Each sample belongs exactly to one of the clusters. Here you see these samples are most likely to belong to cluster 1. These samples most likely belong to cluster 2, but these samples in the margin or the shared area have the equal clustering ability to belong either to cluster 1 or 2. One of the most widely used clustering algorithms is called k-means, and k is a parameter, the number of clusters that we initially decide. So for this figure, let's say we already know that these samples belong to 3 clusters. So we decide this parameter k equal to 3. And we start by putting 3 random centers on the plane and assign each sample to the closest center. So these samples are assigned to this green center. These samples are assigned to this blue center, and these samples are assigned to this red center. And then we move or relocate this center to the center of mass of each cluster. For example, the center of mass or average of X and Y values of the samples in green color is here, in blue color is here, and in each have many different of sample located. Yeah,
Like,
is there?
your connection seems to be breaking. We're losing you a little bit. Anything you can try to do about that? Ali, we've lost your audio completely.
Do you have my audio right now?
Yeah, okay. Now
Okay,
it's
good. Okay, good. Sorry. So there are many different clustering algorithms depending on the style or the shape of the input data, the clustering algorithm that the best matches our data might change. So there is a package scikit-learn in Python that you can simply import, and you can choose your clustering algorithm based on among many different options. The next item is support vector machine. So it is the classical machine learning algorithm that was used for many years for classification of the input data. So the idea here is we are given some samples, but each sample has a given class. And we want to find out a simple line or a hyperplane. And a hyperplane is very similar to a simple line, but in n dimensions when n is above 2. So you can think about this plane in 3 dimensions, and you can think about an equation here in higher dimensions that is separating our samples from different classes into different classes. So the idea is what is the plane or hyperplane or simply line here that has the best classification margins. And by classification margin, I mean the boundary between different classes. For example, if we choose this line here, it is very close to the points here and very close to the points here. So, for example, if a new point arrives here, then we misclasses this new sample as a red class sample, but this is incorrect. So with this given data, the optimal hyperplane would be this one that has maximum margin from the samples of 2 classes. So there is a mathematical notation for it, and we can choose these values of beta such that the margin is optimized. So there might be different problems. The first one would be noisy data. For example, there is a point here that belongs to this cluster or this red class here, and it makes our best classification line here, while we know this is just a noise and we could draw a line here. The other so to handle this problem, we could add soft margin cluster. So there is a parameter C here that we can balance how much we would allow noisy data and how much we would care about the size of the margin. The other problem is whenever our data is non-linearly separable, means there is no line or there is no hyperplane that divides the different classes. And you can see, for example, these two data sets. The blue points versus the red points are not linearly separable. And here we can do a feature engineering, for example, add new features. For example, if our original features are X1 and X2 means the X and Y of the points, we could add somehow, for example, X1 to the power of 2 to the power of 3, or X1 times X2, and this is called feature engineering. So with initial features, we are adding or developing new features such that based on the new set of features, we could find somehow a linearly separable subspace. And this can be enhanced to these kernel functions, and these kernel functions relocate the original samples into a new higher dimensionality space, such that the points were not linearly classifiable here, but they can be linearly separable in the new dimensionality space. So, and the support vector machine can be done in many different ways. For example, whenever we have only two classes and we want to find a binary classification problem, or whenever we have multiple classes and we want to do three classification algorithms, for example, three lines that each line only classifies one class versus the other classes, or we can do it one versus one and find out all combinations of classifiers for each pair of two classes. So to ensure our classification is done greatly, we have different metrics here. For example, whenever you do a classification, a binary classification, for example, given our data is a set of normal or cancer samples, and we have a test. So we already know that there are a group of normal people and another group of cancer patients. And we have a test, and based on the actual state of each person that has negative cancer or positive cancer, and the outcome of our test, which is negative or positive, we can group all samples into four categories. For those true positive samples are those people that have cancer and our test is positive for them. Those true negatives are the healthy people that the outcome of test is negative for them. But we might have false positive cases. For example, those healthy people that the test is positive but wrong, or false negative, those cancer patients that the outcome of the test is negative for them. And we can compute different accuracy metrics. For example, the accuracy is total of these two cells divided to all four cells, which is the number of samples that we correctly identified divided by the number of all samples. And we can compute the sensitivity or recall, which is the number of true positives to true positives plus false negatives. And the sensitivity means how sensitive is our test. Whenever a cancer patient is tested, is our test sensitive enough to make an alarm about a positive cancer patient? And specificity means the number of true negative divided by the true negative plus false positive, or true negative divided by the whole row here. We can also compute a true positive divided by the whole column here, which is called precision. We can compute F1 score. And it's very important that whenever our number of samples are not balanced, actually, for example, 95% of samples are cancer negative, and we have only 5% of people cancer positive. If the test is negative for all of the people, we have 95% accuracy. But it does not mean that our test is something valuable. Our test is simply rubbish because it is assigning every person as negative. So we should, in imbalanced cases, we should care other metrics like F1 score or sensitivity and specificity, or sensitivity and precision and it is called recall versus precision, in order to make sure that the test is working great. So we can assign a threshold, for example, for our test. For example, consider a test of cancer, which have some sort of signal, and we can assign a threshold. Above that signal level, we say the test is positive. And below that signal threshold, the test is negative for patients. And the question is, what is the threshold that best distinguishes between these group of patients? So, for example, here there is an algorithm that assigns a CATness score to each sample. So more score means the sample is more likely to be cat, and less score means more likely the sample to be a dog. And the question is, whenever which one of these thresholds we can assign such that the samples above that threshold are assigned as or predicted as cats. So, for example, here we have 100% specificity, but at the cost of reduced sensitivity. Here we have 100% sensitivity at the cost of reduced specificity. So we might decide here that both sensitivity and specificity, or precision and recall, are great. So we can think about this threshold as some trade-off between sensitivity and specificity, or between precision and recall. And whenever we increase precision, we have lower recall, and vice versa. So we can plot these curves. For example, it is called false positive rate and true positive rate plot. So our idea is the random assignment is simply here. And if our classification method works perfectly, we'll have a curve like this. But in many cases, it is not the curve like this. So if we have this curve with higher area under the curve, it would be better than, for example, this orange one with lower area under the curve. So let's introduce other items of classical machine learning. So a very important item on classical machine learning is loss functions. So you already understood that, for example, in regression problems, there is this mean squared error, which means that the difference between the true value of each sample versus the predicted value to the power of 2, and we compute the mean or average value among all samples. So we have also mean absolute error, which simply we replace this power of 2 to absolute function here, but the mean function is the same, or mean absolute percentage error, or other regression losses. And our problem for regression is simply an optimization, that we have this input data. We want to find the parameters of the model. For example, whenever our model is a linear model, we have this beta 0 and beta 1, which are the parameters of a simple line. And whenever our model is n-dimensional plane or hyperplane or some sort of, for example, polynomial with a degree greater than 1, we have multiple parameters, and we want to find out a set of parameters that minimize the this loss function. You can see these different loss functions have different effects on the our model. For example, if we want to use the mean squared error with small changes or with small errors, we have lower loss value in comparison with when we are using the mean absolute error. But in the larger errors, the loss function for mean squared error is significantly higher than mean absolute error. So depending on the problem, if we want to allow very small errors, but disallow very large errors, mean squared error is a better choice for a loss function. But if we want to disallow even small errors, a mean absolute error might be a better option. And we have these loss functions for classification problems. So whenever we are doing a binary classification, we can think about this binary cross entropy function that, again, yi is here the true label of the point. So each sample or point is labeled as 0 and 1 regarding whether it belongs to class 1 or 2. And this value is the predicted value of yi. And so if both yi and pyi are both this pyi is the probability whenever our model is assigning a probability for the sample to belong to class 0 or 1. This is the probability. And if, for example, the sample is belonging to class 1, and this probability of class 1 is 1, so the log of 1 would be 0, so there would be 0 loss here. But if the sample is belonging to class 1, but the probability is computed to 50%, so log and log is done in base 2, so the log of 50% would be -1, and -1 times 1 would be -1, and because this minus here, we will have a loss of 1 here. If the probability is even less than 50%, for example, it is approaching to 0, so the logarithm will approach to the minus infinity, and times this minus will be plus infinity, so the loss function will increase a lot. So we want to minimize this classification error when we are doing binary classification. So this is very symmetry. So this is just the very same phenomenon, but for the samples that belong to class 0. And we could enhance it to multi-label classification, which is called the simple cross entropy. And there are other functions. For example, this cross entropy is very similar to KL divergence, which is used to compute the difference between two probability distribution functions. So let's start with artificial neural networks. We already studied these support vector machine or other very simple machine learning approaches, but we'll face much harder problems, like whenever we want to classify images and say which these images are cats, the other images are dog, or whenever we have a sentence and we want to decide the translation of this sentence from German to English. And these are much complicated problems that these simple classification or clustering algorithms do not work on it very greatly. So these artificial neural networks are the basis of revolutionized AI performance that started mainly, they started from many decades ago, but they are at the center of focus since 2012, and because they did great in many very challenging problems like image classification. So the idea comes from biology. So whenever you think about a neuron, there are these dendrites that receive the electrical signals from the neighbor cells, and there is one axon that transmits signals to the other cells. And there is a cell body here that is either in firing state or not firing state. You can think about it a neuron as on or off, or as 1 or 0 state. And we can turn the same neuron into this very simple mathematical formulation that you have these inputs. Each input can be simply a number, and we multiply each number to a weight. These weights are parameters to be learned during our machine learning algorithm. So you can think about these inputs as different pixels of an image or different words of a sentence or anything similar to that. And these weights are initially assigned randomly, but during the machine learning, I will tell you how these weights are updated in order to make the correct output at the end. So each parameter xi is multiplied by this weight, and they are summed together, and a bias, which is very similar to the intercept whenever we have a line equation here. So this bias is also a parameter. It could be assigned randomly initially, but during the machine learning process, this bias is also updated. So these values are all summed together, and it undergoes an activation function, which makes the output not linear. So you remember from support vector machine that linearly separable problems are very simplistic, and many problems do exist that they are not linearly separable. So this activation function provides nonlinear activity to our neural network. So there are many different types of activation function. You can see here one very simple choice would be rectified linear unit, which is simply the same value of x whenever x is greater than 0, or 0 whenever x is less than 0. And there could be ELU, leaky ReLU, or tangent hyperbolic, or sigmoid. And this sigmoid function, for example, is the most one of the best choices whenever we want to do a classification. For example, if the value of x is towards -infinity, so the output value would be 0, and whenever the value is towards plus positive infinity, the output value is 1. So this is very similar to off and on state of a neuron, but this shape makes a nonlinear separation. And we have many different activation functions. If you import Torch in Python, you will see many different activation functions do already exist in PyTorch library. So no need that you develop this activation function by hand. So this is very important. This softmax is a kind of activation function for the last layer whenever our problem is classification. So the softmax is one of the most important and widely used activation functions for a multi-class classification. So I talked about updating the weights and how it is done. It is done by a gradient descent algorithm. So we have the loss function here, and we want to find out weights in such a way that they are optimized in minimizing the loss function, and that's the whole idea. And whenever you are located here, you can think about you are standing on a mountain and your goal is to reach the deepest part of the mountain. So if you are looking at the whole landscape, it's very simple to find out the deepest area, but this is not the case whenever we are trying with many kind of different optimization problems that you are staying here, and based on small changes to your weights, you can decide, okay, if I increase this weight, my loss function is increased, but if I decrease this weight, my loss function is slightly decreased. So the best idea here is to decrease the weight. But if we are standing here, by increasing the weight, we will have a lower value of loss function. So the idea is similar to this. So from each position or from each set of initial values of parameters, and by parameters I mean all weights and bias values, we want to find out the gradient there. And the next step is to update these weights, all of the weights. By weight, from here to the end of the presentation, I mean both all parameters, meaning all weights and bias values. So the weight of time plus 1 is the weight of the previous time minus some parameter, which is called the learning rate, times the gradient of the loss function. And the gradient means a vector that is towards the most increased way of increasing the loss function. So minus is exactly in the reverse position, that is decreasing the loss function. So whenever we have a single layer perceptron, and a single layer perceptron means we have these inputs and we have only one layer of neurons that are deciding the outputs based of these inputs, we can do very simple problems. For example, it's very hard or impossible to do many of these classification whenever we do not have a line that perfectly classifies all of the points of two classes. So to solve this, we increase the number of layers. For example, this is called multi-layer neural network, or simply deep neural network. By deep, we mean there are many layers in our neural network. So we start with this input layer. We have a number of hidden layers, and we have one output layer. and the output layer might have one neuron whenever we have a very basic binary classification, or we might have many neurons here in the output layer. And the question is how many hidden layers we might have, or how many neurons in each hidden layer we might have in order to have the best results. The answer is not simple, so it really depends on the problem. It depends on the data, and it depends on many other factors that you might have. So the best way is to look at different best practices, top state-of-the-art models, in order to have an idea what is the architecture of best performing neural networks in this specific problem. And by trying and doing exercises on many different problems, you will have an idea whenever to increase the number of layers, whenever to increase the number of neurons per layer, when in which layers you should choose which type of activation function. And there are many different things that you can play with. It's kind of Lego that you can build many different types or many different architectures of deep neural networks, and some of which work greatly on each problem. So the idea of these deep neural networks while training, and you remember from previous session by Maxime that we have a training data and we have a test data. And by training data, I mean a subset, for example, 70% of all of the samples that I do have that I use in order to decide the best performing parameters and hyperparameters. By hyperparameters, I mean the number of layers, the number of neurons per each layer, the type of activation functions. By parameters, I mean the weights and the bias values. So based on the training data, we update the values of parameters. We can split our data into train, validation, and test data. For the test data, we do not touch the test data until we have fixed the number of hyperparameters, and we have find out the optimal values of parameters. And finally, we go to the test data. But what is the difference between the training and validation data? So we for example, choose 60% of the data for training, 10% for validation, and the remaining 30% for test. So based on 60%, we choose some architecture. Based on this 60%, we update the weights. Based on the rest of 10%, which is called validation data, we evaluate the performance. We might here decide to change hyperparameters, for example, decide to increase the number of neurons or decrease, or increase the number of layers or decrease, or change the activation functions, and do again the whole training procedure on this new architecture of a neural network, and then use the validation data in order to evaluate the new architecture. And we repeat this scenario of training based on the training data and evaluation based on the validation data in order to find out the architecture that is best performing, along with the parameters on that architecture which are best performing. And whenever we are in the final stage of, okay, this architecture is the best, these parameters are already decided, we go once to the test data and evaluate the network on the data that is not seen already by the network. If we go to the test data and alter the parameters or hyperparameters based on test data, we are actually cheating, because our network is already has the results of the test. So the values, the metrics are not reliable anymore. So during this forward propagation, we put the one of the training data here, and we evaluate the number, the value, the output value of each neuron layer by layer, and go on until we compute the outputs. And the predicted output might be similar to the actual output, or might have error here. And the idea is to back propagate the error in order to update the parameters here. And this is the back propagation. So in another backward propagation, we compute the gradients, and the gradients means the derivative of loss function with based on each single parameter in the all layers of the network. And how it is done? So how, yeah.
I'm sorry to interrupt, but we have to end this session pretty soon. If you think you can wrap it up in another minute or two, let's do that. If
I'll try my best to be very rapid. So there are many many very simple ideas. So in the forward pass, we can simply use this chain rule here. So if we already have the derivative of loss based on this output, we can calculate the derivative of loss with respect to x and y by multiplying this del L to del Z times del F to del X, and the F is the activation function here. So it will gives us del L to del X. And the same can be done for del L to del Y is simply del L to del Z times del F to del Y. And we, based on this activation function, we already know the del F to del Y. And we can, in a forward pass, for example, 3 to the power of 2 is 9, and 9 multiplied by 4 is 36, and 36 divided by 2 is 18. And the del F to del F is simply 1, but we can back propagate the values based on this chain rule here to compute all of these values, and based on the very simple gradient descent that I told, we can update the parameters here. So there are many ways of doing it. For example, we can choose a we can give the whole batch of the training data in each iteration. We can randomly select one sample, or we can split the whole batch of data into mini batches and to do it, which provides the best idea, the best results. So we can do it into many different batches in iteration, and we can do the same thing again and again with our training data, which is called epoch. Until 100 epochs, our network might be very well. So I skip the details here, and there are many parameters that we can play with. For example, the learning rate. We can think about overfitting, and we can introduce regularizations or do early stopping, and we can think about many different approaches in order to achieve the best results. And if you want to have the complete slides here, it's simply you can go to my GitHub, and from the slides section, you can have all of these slides along with many other slides. Thank you very much.
Thank you, Ali. We will also share the slides in a link after the via email. after the session. So in the interest of time, I will skip the question session now. We can take questions after the NLP lecture. One comment on YouTube that I can see is, are these lectures for high school students or for university students? Understandably, it's difficult to adapt this kind of material for high school students, and the hope is that the team leaders will take the most essential from today's lectures and translate it as much as possible for the high school students.